Here, our aim is to derive an expression for the intensity of the transmitted and reflected wave in terms of the incident wave. That is our aim. Here, we are interested to find out how much fraction of the energy is reflected and transmitted when a light falls normally on the boundary separating the two media. That is our aim. We want to find out how much energy is transmitted. That is, if you know the refractive index of the two medium 1 N1, medium 2 N2, that is, if you know the refractive index of the two mediums, then you can predict how much energy will be transmitted, how much energy will be reflected back if an electromagnetic wave travels from one medium to the medium 2, one medium to the another medium. For this, we want to know the electric field component in the second medium. If you know the electric field component in the medium 1, magnetic field component in the medium 1, then you can predict the electric field component in the medium 2, magnetic field component in the medium 2 using the boundary conditions. Therefore, to develop the equation to find out how much energy is reflected back and how much energy is transmitted, then to calculate those reflected and transmitted energy, we use the boundary condition, and using the boundary condition, we will write the reflection and transmission coefficient or the reflection or the transmitted amplitude. Then one can easily find out because the incident energy or the intensity of the transmitted radiation or the intensity of the reflected radiation, because the intensity is proportional to the amplitude square. Here the amplitude square means amplitude of the electric field component, amplitude of the magnetic field component. That is a procedure that we are going to do. Is we will apply the boundary conditions. Apply boundary conditions at z is equal to 0. Z is equal to 0 in the sense that is, it is a boundary separating the two media. See, this is a z-axis, positive z, this is a negative z, this is a 0, that is equal to 0, that is our interface. This interface is nothing but boundary. That is, our boundary lies at z is equal to 0 position. Then we know that the general boundary conditions. To apply the boundary condition, we should know what is the general boundary condition. The general boundary conditions in electrodynamics, that is, the first boundary condition is epsilon 1 En1. How do you remember the boundary conditions? That I have said one shortcut, that is continuous benefit. Which means the normal component of the magnetic field is continuous. If you have two medium, normal component of the magnetic field continuous means normal component of the magnetic field medium 1 minus normal component of the magnetic field medium 2, that is equal to 0. Then next, tangential component of the electric field is continuous. That is tangential component of the electric field in medium 1 minus tangential component of the electric field in medium 2, that is equal to 0. All other components are discontinuous. That is, tangential component of the magnetic field is discontinuous. One can easily write that is BT1 by mu1 minus tangential component of magnetic field in medium 2 by mu2, that is nothing but free current density, kf cross n cap. Then another discontinuous component, what is that one? Normal component of the electric field, En1, that is epsilon 1 En1 minus epsilon 2 En2 is equal to sigma f. These are the general boundary conditions in electrodynamics. Okay, in this case, if we consider the electromagnetic wave is traveling from air to water, that is, if EM wave travels from air to water or water to glass or air to glass, then that is, we have the two medium. The medium one is air, this medium one. Then this wave is this is a big block of glass. Then this is our medium 2. It is nothing but a glass. Then this glass is not a conductor. This is an insulator. Therefore, surface charge density will be 0. Then the volume charge density will be 0. And there will not be any free current, because on the insulator or the dielectric medium, there will not be any free current or free charges. Therefore, the Kf, the free current, surface current will be 0, because there is no free charge at all in the insulator medium. Therefore, one can easily write that here the general boundary condition sigma f, this will be 0, and free current, this will also be 0. Okay, that is, in this case, the electromagnetic wave traveled from air to glass or air to water, whatever it may be. That is, the surface which does not contain any free charge or free current. Therefore, here we can write is sigma is equal to 0, Kf is equal to 0. Therefore, the general electromagnetic boundary conditions we can modify in the following fashion. First equation we can write not. If I write the normal component of the electric field, this equation first, this will be epsilon 1 En1 is equal to epsilon 2 En2, because the right hand side of this equation is 0. The second equation that I would like to write here is this one, Bn1, normal component of the magnetic field, that is this equation, Bn1 is equal to Bn2, and the third equation that I would like to write is tangential component of the electric field, that is this equation, Et1 is equal to Et2, and the fourth one is this equation, Bt1 by mu1 is equal to Bt2 by mu2, because the right hand side is 0, no free surface current. That is, these are the boundary conditions that we are going to apply to calculate the reflected and transmitted amplitude. Okay. Then here, what is this E normal and B normal, E tangential components? This can also be written, this boundary condition, in this way also. The few people write this normal component and tangential component in this way, that is, this can be written as epsilon 1 E1 perpendicular is equal to epsilon 2 E2 perpendicular. Both are the same representation. And magnetic field, the second equation, will write P1 perpendicular is equal to P2 perpendicular. That is, perpendicular component of the magnetic field is continuous. Normal component means perpendicular component. Then similarly, E1 parallel, tangential component is represented by E parallel, that is equal to E2 parallel. The fourth equation, B1 parallel divided by mu1 is equal to B2 parallel divided by mu2. Both are the same representations. Okay, now what is this parallel and perpendicular component? That I will show you very clearly. If you refer this figure, the boundary lies along this x and y plane. This is our boundary. Okay, then if you look at this incident wave, electric and magnetic field component, the tangential component or parallel component to this boundary, that is this direction, and these two directions are, or these two axes are parallel or tangential to this boundary. Perpendicular component means that is this one. This is the perpendicular component to this boundary. Okay, then if you check this electric and magnetic field, the magnetic field is along this y direction, electric field is along this x direction, and the propagation vector B is along the z direction. The propagation vector is perpendicular to this plane or perpendicular to this boundary, but y-axis and x-axis are tangential to the boundary. Okay, therefore, in the medium 1, both in the incident wave, this is an incident wave, this one, and this is a reflected wave. Both the incident and reflected wave do not have any electric or magnetic field component normal to the boundary, because this electric field is propagated like this, and this electric field is parallel to the x-axis. This is a tangential component. The electric field is said to be tangential, and the magnetic field meets this boundary in this way. That is, this magnetic field is also parallel to this boundary because this is parallel to this y direction. Therefore, the incident wave does not have any electric or magnetic field component perpendicular to or normal to the boundary. We have only the tangential component. And if you refer the reflected wave also, this reflected wave, the electric field component is still along the x direction, that is parallel to the boundary, and the magnetic field component is oriented along negative y direction. Still, this negative y direction is also parallel to the boundary. That is, there is no normal component of the electric or magnetic field in the reflected wave component also. Therefore, I can write here, in this case, there is no En, this normal component of the electric field, or magnetic component of the electric field at z is equal to 0, because at z is equal to 0, the boundary lies at z is equal to 0. There is no normal component of E or B. Therefore, the boundary conditions can be applied only to the tangential component. Therefore, we have to consider these two boundary conditions. Okay. Let me write all these factors here. Only E tangential and B tangential components are present. Therefore, we have to apply the boundary condition for ET and BT. For E tangential and B tangential at z is equal to 0. If I write down the boundary condition, this is the boundary condition 1, this is boundary condition 2, boundary condition 3, boundary condition 4. Here the boundary condition 3 and 4, that is the boundary conditions, means here we can mention the boundary conditions 3 and 4. Apply boundary conditions. B.Sc means boundary conditions 3. Then at z is equal to 0, that what are the boundary conditions we have to apply? E tangential 1. The third boundary condition means here, that is E tangential 1 is equal to E tangential 2. Then what are the tangential component of the electric field present in the medium 1? That is the meaning of ET1. Total tangential component of the electric field present in the medium 1. If you refer this figure, here you can see that the tangential component we have of the electric field, we have the incident electric field component and the reflected electric field component. That is, totally we have the ET1, I can write EI ZT is equal to, in the second medium, the tangential component. What is that second medium tangential component? Tangential component, we have the transmitted amplitude of the electric field, that is ET. This transmitted wave, transmitted electric field, ET ZT. What is the expression for the EZT? That is, if you go back, that is we have written here. That is if you look at this expression, this is a expression for the electric field, incident electric field. Then we have to apply the boundary condition. Boundary condition means our boundary at the interface, that is this boundary lies at z is equal to 0. Therefore we have to put this z is equal to 0 here. Then EIZT, I can write E0I into e power minus I omega t. That I have to write. Similarly, for the transmittal electric field, this one, what do we have to write? This I can write, instead of E transmitted ZT, I can write E0T. Here we should have the complex amplitude. E power, here Z is equal to 0 because our boundary lies at Z is equal to 0. This will be e power minus I omega t. Okay, now I am going to, instead of EIZT, I will substitute E0I e power minus I omega t. ETZT, I will substitute E0T e power minus I omega t. That is, here I will write E0 I plus, okay, one more thing I want to mention here. The medium one, we have to take the whatever the electric field components is present. That may be either in the incident wave or that may be present in the reflected wave also. In medium one, whatever we have the tangential component of the electric fields, all those electric fields have to be taken. Therefore, if you go back to the picture, here the reflected wave, this is a reflected wave, that is also having an electric field component. Therefore, here I want to, this is not correct. Here we have to write the medium one, we have the two tangential component of the electric field. First one is E incident, is EZT plus ER ZT equal to ET. Because in the second medium we have the only one transmitted wave, but in the medium one we have the two wave, one is incident and another is transmitted. Therefore, similarly, if I apply z is equal to 0 in the expression for the reflected electric field, this will be E0 I minus I omega t plus E0 R e power minus I omega t is equal to, then E transmitted already I have shown, that is E0 t e power minus I omega t. That is e power I omega t, e power minus omega t will be cancelled. The final one is E0 I plus E0 R is equal to E0 t. This is equation number 1. Now, as I mentioned earlier, there is no tangential component, normal component of the electric field, magnetic field. We apply the boundary condition only for E tangential and B tangential. We have already applied boundary condition for the tangential field. Next, we are going to apply the boundary condition for the tangential component of the magnetic field. Then, what is the tangential boundary condition for the magnetic field? That is, you come back to this fourth boundary condition. That is a boundary condition for tangential component of the magnetic field. Then first I will write here, that is, apply boundary conditions. Short I will write B.Sc for tangential component of the magnetic field. Then, that is, it is nothing but the fourth boundary condition, this one, boundary condition for, can be written as Bt1 by mu1 is equal to Bt2 by mu2. Then once again you come back to the picture, that in the picture it is very clear that what are the tangential component of the magnetic field present. Here we have two waves, one is the incident wave, this is the reflected wave, and the medium one we have two tangential components, that is Bi and also the Br. Therefore, I can write in the medium one, if we apply the z is equal to 0, also here also I have to put z is equal to 0. Then e power ikz minus omega dz will be 0, e power minus I omega t will be there. Then if I write the both side, that will be cancelled out. Finally, I am going to write this quantity, that B0 I divided by mu1 minus B0 R, because we are reflected component also in the medium one, by the mu1, because reflected wave also lies in the medium one, that is why both have the mu1. Next, the transmitted amplitude of the magnetic field B0t, transmitted wave lines the medium 2, that is why mu2. Okay, you know the relation. You can write this magnetic field in terms of the electric field, because B is equal to 1 by V1 into E. That is I can write this as a expression E0I by V1 mu1 minus E0R by V1 mu1. Similarly, for the transmitted magnetic field, E0t by, since it is a medium 2, we have V2 mu2. Okay, then here I will do small algebra, that I will take 1 by V1 mu1 outside, then this quantity will be E0I minus E0R is equal to E0t divided by V2 mu2. Then once again, if here I can take few quantities outside, that is, I can keep E0I minus E0R on the left side. If I take this V1 mu1 to right side, this will be V1 mu1 divided by V2 mu2 into E0t. I am going to make a slight changes. That is, I am going to write this, I am going to replace this V1 and V2 in terms of the refractive index, because that will be quite easy. If your wave is traveling from air to a glass piece, the refractive index of the air is known, N1, refractive index of the glass is known. Then if you know the refractive index, we should calculate the energy, how much energy will be reflected, how much energy will be transmitted. That is, you need to know only the N1 and N2. In that form, we have to derive our expression. Therefore, instead of V1 and V2, V1 is the wave velocity in medium 1, V2 is the wave velocity in medium 2. Calculation of this wave velocity is quite difficult compared to the refractive index. Refractive index one can easily know. One can easily get the refractive index. Therefore, how I can connect the velocity into the refractive index? That is, we know N1 is equal to C by V1, because refractive index is nothing but C by V. Similarly, N2 is equal to C by V2. Therefore, N1 by N2 is equal to C and C will be cancelled out. This will be V2 by V1. Therefore, here we have V1 by V2. Therefore, take the reverse. V1 by V2 is equal to N2 by N1. Therefore, just to replace this V1 by V2 by this N1, N2 by N1. Therefore, here I can write this E0I minus E0R, that is equal to V1 by V2 means N2 by N1 and mu1 by mu2 E0t. Okay, instead of writing this N2 mu1 by N1 mu2, what I am going to do is here I will take this as a beta. Then I can easily write this expression as E0I minus E0R is equal to beta E0t. Okay, let me put this is equation number 2, where beta is equal to N2 1 divided by N1 mu2. Now I have obtained the two equations. That is, the first one, applying the third boundary condition, I obtained the equation 1. Then applying the fourth boundary condition, I obtained equation 2. Then I will write these equations together. That is, the first equation was E0I. As I mentioned earlier, our aim is to calculate the reflected and transmitted amplitude of the electric field in terms of the incident amplitude. Therefore, from this you can easily you can do it. That is, if you add equation 1 and 2, then the reflected amplitude will be cancelled out. This will be 2E0I is equal to, from E0t I can take it outside, then this will be beta plus 1 E0t. Okay, Or from this it is clear E0 T can be written as compressed amplitude of the transmitted electric field, that is 2 by beta 1 plus 1 or 1 plus beta into E0 I. This is the first result. This is the amplitude of the transmitted electric field in terms of the incident electric field. This is nothing but the transmitted amplitude. Let me put this is equation number 3. Nothing but transmitted amplitude. This is not the real form. This is the complex form, because here we have a like this complex notation. Now I want to calculate the reflected amplitude. For this I do the calculation here itself. I need to calculate reflected amplitude. What do we have to do? Put this equation 3 in equation 1. First, here we have this E0t. Replace this E0t by this equation 3. Put equation 3 in equation 1. That is E0i plus E0r, that is equal to, instead of E0t, we have to put equation 3, that is 2 by 1 plus beta into E0i. നമുക്ക് ഇനി എന്ത് ചെയ്താൽ മതി? E0r നിർത്തിയാൽ പോരെ? E0r നിർത്തി കഴിഞ്ഞാൽ ഇന്നത്തെ ടൈമിന് അങ്ങോട്ട് കൊണ്ടുപോയി കഴിഞ്ഞാൽ E0i പുറത്തേക്ക് എടുത്തു കഴിഞ്ഞാൽ 2 by 1 plus beta minus 1 into E0i എന്ന് കിട്ടും. ആൾജിബ്ര ചെയ്ത് കഴിഞ്ഞാൽ വളരെ ഈസി ആയിട്ട് നമുക്ക് ഒന്ന് പെട്ടെന്ന് ചെയ്ത് നോക്കാം. E0r is equal to 1 plus beta minus 2 minus 1 minus beta into E0i. Then this E0r is equal to 2 minus 1 minus beta means 1 minus beta divided by 1 plus beta into E0i complex amplitude. This is very clear that this is expression for the complex amplitude of the reflected electric field in terms of the incident electric field. This is the reflected amplitude. If you compare these results with that we already derived in the case of the waves on a string, the results are striking. The results are similar to the ones for waves on the string. Therefore, I write here the results are similar to the ones for waves on a string. Okay. Now here I am going to make a few changes. That I am going to replace this beta in the reflected amplitude of this equation, and also the in transmitted amplitude, that is in equation 3, I am going to change this beta. Both beta I will rewrite in terms of the velocity. Okay. Why we are going to rewrite in terms of the velocity? In the case of the string, we have learned that if we have the two string, one is having lighter mass and is having heavier mass, then if the wave is traveling along this direction, it will be reflected back. The phase will be out of phase, and the wave velocity will be different, v1 and v2. If v1 is greater than v2, then there will be a phase change in the reflected wave, and those discussions we have already done. Now let us connect those results in the case of the string with these new results. Okay. That is to write in terms of the wave velocity, I am going to change this beta into in terms of v1 and v2. That is beta, what substitution we have done. If you see here, we have written the beta is equal to n2 mu1 by n1 mu2. Here what I will do is, if I write n2, this n1 by n2 is v2 by v1. This can also be written as v1 mu1 divided by v2 mu2. Therefore I will use this notation. I will rewrite our expression in terms of this one. This I will replace all this beta in terms of v1 mu1. This beta I will write v1 mu1 divided by v2 mu2. And one more thing I would like to mention here, that the permeability of the two medium, that will be approximately equal to same. This mu1 is equal to mu2. This beta reduces into v1 by v2. That is, this is the new beta that I am going to substitute both in the reflected and the transmitted amplitudes. Therefore, E0t can be written as 2 by 1 plus v1 by v2 E0 I. Let me put this is equation number 5. E0r. E0r you have here, that you can be, this can be written as E0r is equal to 1 minus beta, we can write v1 by v2 divided by 1 plus v1 by v2 into E0 I. If I rearrange the terms, I will get E0 R is equal to v2 minus v1 by v2 plus v1. The denominator to v2 will be cancelled out, and E0 I. This is equation 6. Okay, let me put this equation in box. These equations are identical to the case of waves on string. If you see the equation 6, that is, if v2 is greater, that is equation 6, this one, if v2 is greater than v1, then the reflected wave is in phase, and if v2 is less than v1, there will be a negative sign, that is reflected waves will be the out of phase of the incident wave. Let us note those two situations also, cases also here. That is, from equation 6, we can write, if v2 is greater than v1, then that whole time is positive, that is, the reflected wave is in phase. Similarly, the reverse, if v2 is less than v1, this result will be negative, equation 6, that is E0r, that will be negative of quantity of E0 I, that is, the reflected wave is out of phase. അല്ലേ? E0യുടെ ഇൻസിഡന്റ് വേവിന്റെ നെഗറ്റീവ് എന്ന് കഴിഞ്ഞാൽ അതിനർത്ഥം റിഫ്ലക്റ്റഡ് വേവിന്റെ ഫേസ് ഡിഫറെൻ്റ് ആണെന്നർത്ഥം. അതായത് ഇങ്ങനെ വരുന്ന വേവ് ഇവിടെ എത്തിയിട്ട് തിരിച്ചു പോകുമ്പോൾ ഔട്ട് ഓഫ് ഫേസ് ആയിരിക്കും അർത്ഥം. Reflected wave is out of phase. Okay. Now you understood the situation. Then you can write the reflected wave is out of phase. Okay. We have the written this equation 6 and equation 5. These are not the real amplitudes. These are the complex amplitude, because you can see there is a complex notation. And what will be the real amplitude? Now that I am going to write here, the real amplitude of the reflected wave, these the real amplitudes are E0R, that can be written as, we have the equation 6 for E0R, that is V2 minus V1. We have to take the modulus, that is V2 minus V1 by V2 plus V1, take the modulus, then you will get the real amplitude E0I. And equation for the transmitted amplitude E0T. See here that here I have not written the complex notation because these are the real amplitudes. The real amplitude, that is, if I rewrite this equation, this can I can write E0T is equal to, if I take the V1 above, this will be 2V2 divided by V2 plus V1. Actually, I forgot to rearrange the time like this. You please do it at the respective place. Then this is nothing but our equation 6. I am going to write, because there is no negative sign here, therefore simply you can take the modulus, or if you are writing without modulus, that also fine. Therefore the transmitted amplitude is equal to 2V2 divided by V2 plus V1 E0I. These are the real amplitudes in terms of the velocity. Now the real amplitude in terms of the refractive index. How I can write the refractive index? Because you know the relation connecting the refractive index and V1 and V2. So I can write E0R is V2, you can easily write N1 minus N2 divided by N1 plus N2. Okay, here he should take the, because here we have written the real amplitude, therefore you have to take the modulus E0I. And similarly for the transmitted amplitude, that will be 2N1 divided by N1 plus N2 into E0I. These are the final results. It is clear that if you look at these two expressions, if you know the refractive index of the two medium, where the electromagnetic wave travels in the medium 1 and enter into the medium 2, maybe this may be glass, this is medium 2. Then if you know the electric field intensity in the medium 1, then you can predict amplitude of the electric field that is reflected back. You can find out the E0R. Only thing you need to know is the refractive index of the two medium N1 and N2 should be known. നമുക്കെന്നെ പറയാൻ പറ്റും, നമ്മൾ ഗ്ലാസ്സിലേക്ക് ഇലക്ട്രോമാഗ്നറ്റിക് വേവിനെ ഷൂട്ട് ചെയ്യുകയാണെങ്കിൽ എയർ റെഫ്രാക്റ്റീവ് ഇൻഡെക്സും ഗ്ലാസിൻ്റെ റെഫ്രാക്റ്റീവ് ഇൻഡെക്സും നമുക്കറിയാമെങ്കിൽ, അതുപോലെ തന്നെ ഇൻസിഡൻറ്റ് ഇലക്ട്രിക് ഫീൽഡിൻ്റെ ആംപ്ലിറ്റ്യൂഡ് ദാറ്റ് ഈസ് അതും നമുക്കറിയാമെങ്കിൽ ഹൗ മച്ച് ദ റിഫ്ലക്റ്റഡ് ഇലക്ട്രിക് ഫീൽഡിൻ്റെ ആംപ്ലിറ്റ്യൂഡ് നമുക്ക് കണ്ടുപിടിക്കാൻ പറ്റും. നമുക്കിത് എങ്ങനെ കിട്ടിയിരിക്കുന്നത്? ദിസ് റിലേഷൻ വി ഒബ്റ്റെയിൻഡ് യൂസിങ് ദ ബൗണ്ടറി കണ്ടീഷൻ. പിന്നെ അതേപോലെ ട്രാൻസ്മിറ്റ് ചെയ്ത് പോകുന്ന ഇലക്ട്രിക് ഫീൽഡിൻ്റെ ആംപ്ലിറ്റ്യൂഡ് നമുക്ക് കണ്ടുപിടിക്കാൻ പറ്റും. ഇഫ് യു നോ ദ റിഫ്രാക്റ്റീവ് ഇൻഡെക്സ് ഓഫ് ദ മീഡിയം 2 and the റിഫ്രാക്റ്റീവ് ഇൻഡെക്സ് ഓഫ് ദ മീഡിയം 1 and also the incident in the amplitude of the incident electric field. അപ്പോൾ ഇവിടെ നോക്കൂ നിങ്ങൾ, ഇതൊക്കെ ആംപ്ലിറ്റ്യൂഡാണ്. ഈ E0 R, E0 I ഇതൊക്കെ ആംപ്ലിറ്റ്യൂഡാണ്. ആംപ്ലിറ്റ്യൂഡ് അറിയാമെങ്കിൽ the intensity of the radiation that is reflected back and transmitted അത് നമുക്ക് കണ്ടുപിടിക്കാൻ പറ്റില്ലോ, because intensity is proportional to the amplitude square. Okay, that is our next discussion.